how do we figure out what atmospheric pressure is? So atmospheric pressure is the pressure you're feeling right now. If you're in your office, or if you're at home or wherever, you feel atmospheric pressure. That's what we're feeling. We don't actually experience it, but it's there. How do we determine what the atmospheric pressure is? And how do we know what that number is going to be? Is going to depend on this little device that we have here. So what this is Hg. Hg stands for mercury. You've got a vat or a pool of mercury right here. And you take a tube and you fill it up with mercury. And like you fill it up with mercury, you hold it down, and then you turn it around and you put it inside this pool right here. And you see how far the mercury will drop. So from the highest point of the mercury that's still left to where it falls down, that's what we're interested in that height. And that height will actually tell us what the atmospheric pressure is going to be. Okay, so how do we determine H? We know that the atmosphere in the pool right here at the top is just the atmospheric pressure. But what about the pressure right there in that point right there? So that pressure is taking all of this mercury going down right there. So we have this pressure right there. This pressure and this pressure that's right here is going to be exactly the same. That's, what's that guy's name? Pascal's principle. The pressure is going to be the same no matter where you are. And so what we could say is at P1, the pressure at P1 is going to equal the pressure of the atmosphere. And from there, we have an equation for P1, pressure from the last day's worth of lectures was equal to the density times gravity times H. Okay? And what is the density? It's the density of mercury. The density of mercury is given by 13,600 kilograms per meter squared. And that's going to equal the atmospheric pressure. And let's just say we're looking at it at the average atmospheric pressure, which is 1,000, what is it? 1,100, 100, and 1,300 Pascal. So from here, we can solve for H. We divide both sides by the density, which is the density of mercury. It's 13,600. And we divide it by G, 9.8 meters per second squared. And so when we do that, we get the height. The height here is equal to 0.76 meters. 0.76 meters. So that is the height that this is going to drop by if you had a set of mercury here. It would fall by that much. And this is how we measure pressure. So if we know the height, we can tell you the pressure. I kind of worked backwards, and I said that this is what the atmospheric pressure is, but this could really change. So what we do is we start off with the standard height, which is this much, and then we compare it to other different heights that it falls by. Another unit that we can use for atmospheric pressure, 1 atm, is equal to this value right here in millimeters, 760 torrs. So that's another unit for 1 atm. And that comes from Torricelli. That's the guy who did this experiment right here. Okay, so this is a device to measure the atmospheric pressure outside. You can't do this now because it's mercury, and you don't touch mercury because it's mercury. There's a lot of fumes that come from there. But in the olden days, they would do experiments where they would actually turn this, and then you'd see it drop. You could measure the height, and then from the height, you could figure out what the atmospheric pressure would be outside. And you should know that the atmospheric pressure, this is kind of the average, just like gravity is 9.8, but it's not 9.8 everywhere on the surface of the Earth. Similarly, the atmospheric pressure is not this value on all surfaces of the Earth. Lower surfaces have lower pressure or higher pressure. Higher surfaces, like on a mountain, have lower pressure. So if you were to repeat this experiment, let's say undersea or versus on the top of Mount Everest, the height would change because the atmosphere on Mount Everest is different than the atmosphere at, let's say, the Mariana Trench. Okay, so that's that. The next thing is using this idea right here we just talked about from Friday's lecture, which was finding the pressure on a wall. Here you have a barrel. This is a big barrel. It's a pretty big barrel. It's 1 meter in height. And what we're going to do is we're going to stick a straw through here. And this is something really, really cool what happens. After I'm done explaining it, I think I attached a video along with this video that you're watching. I sent a link, and the link has a video of this actual experiment happening. And it was done by some professor at Princeton. I don't know if you know about Princeton, but it was done by them. And nobody actually has repeated this experiment before. So it was the only video I saw on YouTube that actually does this experiment, and it works. So what you do is you take a barrel right here, and you can take a straw. It doesn't have to be very thick. It could be as thin as you want, and you're going to pour water into it. Now, it's got to be a very long straw, but you can put water into it, and not a lot of water either. So imagine if this carried like 400 gallons. You could take a straw that's very long and put maybe half a gallon of water into it, and that pressure from that straw with the water going down is enough to break the barrel. Think about that. Half a gallon breaking a barrel. That doesn't make any sense, but it does. So what we want to do is we want to figure out the force on the wall of this barrel right here. We're given the height of the barrel, we're given the radius of the barrel right here, and we want to find the force. Well, we can find the force by using the equation. Force is equal to the average pressure multiplied by the surface area of the barrel. In this case, it would be the inner surface area. So how do we find the average pressure? The average pressure is given by the equation rho g times y. And the pressure we're interested in is at this height right here. Okay? So this is the average pressure, the point that we're interested in. So it's all of this and then in the middle point somewhere right here. And so I could write this as, well, we're going to multiply it by A as well. This could be written as rho of the water times gravity times all of this height, which is h1, plus the height over here, the average height here. And that's going to be h2 divided by 2. So that's the average pressure. And what about the area? The area is just the area of the inner wall plus the top and the bottom plates. So we're looking at the entire surface, the inner surface area. So it'd be the cylinder sidewall plus the flat plate on the top and the flat plate on the bottom. So we have to add those areas together. So we're going to multiply that by A, where A is going to equal the round part right here, which is, what is that? The circumference, 2 pi, what's the circumference? Pi, no, it's 2 pi times the radius, which is big R, squared times the height, h2. And we're going to add to that plus the surface area of this top plate and the surface area of the bottom plate. So that would be 2, because there's 2 of them. 2 times pi big R squared. Okay, so that's the inner surface area of the whole thing. It's this plus this, and we're going to multiply it by this term right there. So when we plug in those numbers, the average pressure is going to equal 2,900 Pascal, and we're going to multiply that by the area, which is going to turn out to be 1.86 meters squared. And we multiply those values together, and we're going to get 373,674 Pascal meters squared, so newtons. Now, what is this value in pounds? We can change it into pounds here, and pounds, it's going to equal 83,000 pounds. Think about that. By just adding this tube that's 20 meters high, and that's all that mattered. It didn't matter what the volume of this thing was right here. All that matters to find this pressure was the height, how long it's going to be. So the longer this tube is, the more force that's going to be exerted on this barrel here. And that force is going outwards in all directions. So there's a force going up, down, left, right, side to side, everywhere inside the barrel. And it's going to push outwards. So it's going to try to explode this barrel. Will the barrel explode? Well, you have 83,000 pounds of force on the inner walls of the barrel. That's equivalent to 41.5 tons. So yes, it will actually blow. That's way too much force on each side of the wall, and it'll actually burst your barrel. And I believe there was a rumor, I don't know if it's true or not, but he made like a bet. The guy, I think it was Torricelli, or maybe somebody else. I don't remember. The guy who created this, maybe it was Pascal. So he would do this experiment, and then he would like bet people, be like, hey, I could just take this tube right here, put some water in there and blow it. And people would be like, no, you can't. And he would do it, and the physics works here. It'll actually explode the thing. So there's that. Okay, what's next? A pressure gauge. Okay, suppose you have this horseshoe-shaped tube. Suppose you have this horseshoe-shaped tube, like so, and you fill it up with, what are we going to fill it up with? Mercury. So there's going to be mercury on this side. We're going to just pour it in, and then it's going to be an equal amount on this side. Okay, so the mercury is going to fill up, and that's what you have. So everything is great. So far, the difference between these two heights is exactly the same. We're good to go. Now, suppose I was to put water right here. If I put water here, what's going to happen is the mercury is going to rise a little bit. And then on the other side, right here, we have water. So we use blue. And the water is less dense than mercury, so you're going to have to put more water in. And you're going to be like that. Okay? So you put water in, and the mercury on this side will rise a little bit, and then the water will rise up differently because they have different densities. And what I want to know is what the difference in the height is from this plate to this plate. What is the difference in height, delta H? Okay, so let's put some numbers in. Let's say from the bottom right here, the height to here, we'll call this y equals 0. This is H1. And H1 is equal to 15 centimeters. 15 centimeters. So that's H1. And then from the same height value here, the height of this is H2. We don't know that. I mean, if we knew that, then we could just take the difference between the two and we would know the answer. So we only know that the height of the water is that big. And we want to know what the pressure difference is going to be. So this is mercury and this is water here. Something interesting is this fluid is static. So that means the pressure here and the pressure here at the same height, since this is mercury, the pressure at this point, we'll call it, what do we want to call it? We'll actually call the pressure right at the surface. So the pressure right there, which is P1, is going to be the same pressure right here, P2. They're going to have equivalent pressures because they're both mercury there. And so using our equation for Pascal, P1 is going to equal pressure 2. Pressure here is going to equal the pressure at that height right there, the same base height. And so pressure 1 is the density of water, H2O, times G times H1. And that's going to equal the density of mercury That's P, what is it, Hg, times gravity times H2. And then from here, the gravity terms will cancel out, and you can solve for H2. H2 is going to equal the density of water, H2O, divided by the density of mercury, Hg, multiplied by H1. So we know the density of water is 1,000, the density of mercury is 13,600, and H1 is equal to 15 centimeters. If we plug all those values in, I guess I could write it out. 1,000 divided by 13,600 multiplied by 15 centimeters will give us 1.10 centimeters. So that's the height, H2, 1.1 centimeters. And if you want to know what the delta H is, you just take the difference between them. The absolute value is fine. So H1 minus H2, and that's equal to 13.9 centimeters. So that's an easy question to do. You just set the two pressures equal to each other there, and you should be able to solve that kind of question. Pretty straightforward. Okay, the last thing, keeping these short now, I want to talk about the thing that I've been using, but I haven't really mentioned where I got it from, which is buoyancy. So I've used buoyancy a few times, but where does that equation come from? I said I would derive it at some point, so might as well do it now. Let's say we got a tank here, and inside the tank you have a cube. There we go. We have a cube there, and there's going to be a pressure at the bottom, which we call P lowercase b, and that pressure is going to cause a force going upwards. There's going to be a pressure at the top, we'll call P lowercase t, and it's going to cause a pressure going down, a force going down. So there's a force going up, there's a force going down, there's forces on the walls, on the sides, but those are equal, so they cancel out. And we're inside this tank right here. So what are some things that we know? We know that the pressure at the bottom has to be greater than the pressure at the top. That's one thing. And if that's true, then the force at the bottom is going to be greater than the force at the top. So that's also going to be true. And then if we want to know what the buoyant force is, the buoyant force is the resultant of these two forces. So the buoyant force, FB, is the net force of these two forces. So it would be the force from the bottom minus the force from the top, because they're pointing in opposite directions. And so what's that going to equal? Well, the force at the bottom is going to be the pressure at the bottom times the area of our object, minus the pressure at the top times the area at the top. And they're both the same area, so we can factor out the A. Pressure, there's an equation for pressure. Pressure is going to equal the density of water times gravity times the height at the bottom minus the density of water times gravity times the height at the top, multiplied by the area. So I just factored out the area from this equation here. And then from here, you could factor out the density of water and gravity, because those are constants. And so we get the buoyant force, FB, is going to equal the density of the fluid times gravity multiplied by delta or y at the bottom minus y at the top multiplied by the area. And so this is just delta y. So we get density times gravity times delta y times area. And you should know that the delta y is just the height between these two right here. You know, it could be at any delta height that you want it to be. And so that's going to be the volume. So we get density times gravity times the volume of the fluid, and that is the buoyant force. And this is the density of the liquid, not the density of the solid. So from here, the last thing we can analyze is that density is equal to the mass divided by the volume displaced. So we could say that density is the mass of an object divided by the volume that's of that object times gravity times the volume displaced, and this is the mass of the liquid or fluid. So the volumes cancel out, and you get the mass of the fluid times gravity is equal to the buoyant force. And so what is the buoyant force then? Well, m times g is just weight. So we would say it is the weight of the liquid that is displaced. The weight of the fluid displaced. So all the fluid that got pushed out, the weight of that fluid that got pushed out is what we call the buoyant force. All right, so that's everything for today. Kept it short, kept it pretty straightforward. And the next lesson will be on Friday because Wednesday I've got to give another test. So until then, adios, cowboy.